Okay. Yeah, I think it should be invariant into one of the directions. I'm not sure if I can figure it out now.
But how does that show up in your general discrete state sheets?
Yeah, it should have the same property, I think. But yeah, I would have to sit down and think which direction it is. Yes. Okay. So now let's look at zero sets. So F is smooth if covariance H is smooth. This is some general random field theory which you can find from textbooks or Adler's book on random fields, for example. So we are interested now only on the very smooth case, so that shouldn't pose us problems. So another fact from textbooks is that zero sets of those guys are isolated points. And probability that Fz is 0 and this is the Jacobian determinant, is 0. This is 0. Okay? So at each 0 should be non-determinant in the sense that the Jacobian is invertible at the 0. Now, if you think of Gaussian analytic functions, then it's not a miracle that, or very surprising that the zeros are isolated, because analytic functions have isolated zeros. In general, my functions are not holomorphic, so here it's due to the randomness of the situation, which forces this. To give you some kind of intuition why this would be the case, that the zeros are isolated, if you think what needs to happen if 0 would be a little curve, for example. So suppose that there's a curve 0. That would mean that both the imaginary part and the real part have to be 0 at the same time on this curve, to have, so that complex valued function would be 0. But if there is sufficient randomness, the condition is that at each point the function has a complex, like smooth complex distribution, which it has in this case because these are complex Gaussian random functions, then the real and imaginary parts cannot cooperate so much. So they are not completely entangled what they should be in order to have a curve 0. So they are sufficiently independent of each other so that this cannot happen. So that forces the zeros to be isolated. And well, it's the same thinking which in fact forces this Jacobian to be invertible at the 0. So if you have that Jacobian is non-invertible at the 0, then there's a direction where at the 0 where it continues to be almost 0, the direction of the eigenvector of the 0 eigenvalue. So yeah, but this can be found in Adler random fields and geometry, for example. Adler-Taylor, right? Okay. So in fact, this fact that the zeros are isolated follows from this, because inverse function theorem tells us that if this is not zero at the zero, then it's locally invertible mapping, and then there can be only one zero in there cannot be a curve zero. Okay. So another object of interest can be a winding number. Of a zero. So we define it as kappa z, and it's a sign of the determinant of this Jacobian matrix at C. So it means that if I have C, which is a zero, and I take a little circle and go it around it, then if it's plus, then I travel to the same direction around the zero, and then or if it's minus, then I reverse the orientation. Okay. So now we want to look at two things. So we are interested in the zeros of this Gaussian Weyl-Heisenberg functions. So one way to do it is take a bounded set B, and then we count the number of zeros in the set. So that's one way to understand the zeros. We count number of zeros in sets and try to understand this random variable somehow. But it is also natural to look at the signed version of this. So then it's like that we sum these charges or winding numbers. No, it's the B. So this we think is like a total charge of the set B. So all zeros have come with the sign plus or minus, and then we just sum them up. And this is this random variable n plus minus b. So we want to study these random variables for some sets B. And the standard way to do this is to get some information is so-called Katz-Rice formula. I think Günther talked about this stuff last week. I just tried the very heuristic versions. I put quotations here because what is going to be on the right hand side is not very well defined maybe. But I have delta evaluated fc times that dfc and same for plus minus thing, but then I don't have absolute value around the determinant. Okay, I suggest that we don't think too much how these things are defined. So some intuition why this would hold. So let's look at this guy. So and look at this expression, and suppose that we integrate this on some little neighborhood around a 0 of f. So just restrict the integral on a little ball around 0 of f. Then you can make a change of variables. Fc equals w. Then you will get w here, and then this will be the Jacobian of the transformation. So when you make this change of variables, then you will pick only one from that little number 1 from that neighborhood, because there is only one 0, so you get just delta evaluated at 0 from that little neighborhood. And then you're going to do the same thing around each 0. And then you will see that in fact this expression is going to be equal to the number of zeros at b. And the second expression, well, the sign of the determinant of TFC is going to, you would have it appear here as a like a factor here. But then the sign will undo the absolute value. So that makes the expression look like this. And in fact, it turns out that this is nicer to work with. The absolute value creates some problems for you. It's more difficult to understand. So, okay. So these are a bit formal, but these representations are quite useful when you try to compute the moments of these random variables. So, for example, expectation. Expectation of NB is going to be expectation of that, and then we commute the integral with the expectation. So then this is integral over b of expectation delta naught fc times this. Okay. So this is already a little bit better. Now I will have to erase some stuff. I hope you can still see something, even though there's some white color on the background. So now this thing inside the integral, this expectation, this is going to be this is of course the 1 point intensity, rho 1. And it will turn out that this is actually a nice function, in fact, a constant. So this rho 1, we can compute. Now it starts to look already a bit better. So this can be computed with the covariance matrix of f with its and the two derivative f to x dx of f and dy of f. So just write the formula. So gamma, I'll write you what gamma is. So gamma z is the covariance matrix of this random vector. X derivative fc, x derivative of fc, and y derivative of fc. So in fact, here we use that this Jacobian determinant equals imaginary part of fx times fy bar. So this is nice in the sense of being explicit expression, and we can of course here reduce the dimension. We can just put the w1 variable to 0 here because of the delta, and then I have integral over c2. Now it's over c3 still. Then it's a matter of evaluating this. So so the gamma z can be computed in terms of covariance kernel of f. So this is good. It's explicit expression now. This is the same holds for charged one-point intensity. I won't repeat this expression. It's the same without absolute value, and that expression will be also the same, but just without absolute value. Okay, good. So now I will write our little result with Günther and José Luis. So as a first step to understand this nb and n plus minus b, we try to compute these integrals to see how they depend on the covariance, or how. So I just write you the special case where we are in this short time Fourier transform setting. So SDFT setting only. In the paper we have that more general, but I won't overwhelm you with. I tried not to overwhelm you with big expressions. So I assume G is real valued, and G has norm 1, and this is 0. So this can be, you can arrange this by shifting G if you want. So this is not a serious restriction. Also, we can do complex valued as well, but I just write down the real valued case here. So then the rho 1 is as follows. It is 4 times C2 C3 plus 1 over 4 C2 C3, where C2 is T squared G squared integral, and C3 is G prime squared. That's the rho 1. Yes, and rho plus minus 1. So this is constant. That constant. So, and this is another constant, which is 1 over pi. Okay. So so here we see some dependence on the window. Some dependence. Here it's independent of the window. So this is always, whatever you choose, you get this intensity of charges. And this dependence on the window is quite interesting. We have Heisenberg uncertainty principle. Heisenberg, yes, uncertainty. It says that C2 times C3 is bigger than 1 over 4. And then we can plot this function. This is y for x plus 1 over root x. And here I have a global minimum 1/4. So this is increasing function after this point 1 over 4. So this tells you that this expression rho 1 is minimized for a Gaussian, because that's what minimizes this product C2 and C3, and then it's like this increasing function of the this product uncertainty, if you want to call it that. So, for example, if you take Hermite function window which has very high degree, this means that this product is going to be very big. So then you observe, if you take a bounded set B, then you are going to observe a lot of zeros, but maybe you have a million zeros. Then you are maybe you have million one zeros, so that 500,000 plus 1 are positive and 500,000 are negative. That's what you this result says to you, like heuristically. So the pluses and minuses always add up to 1 on a set, in expectation, of course, in expectation on a set of volume 1. So there is a big cancellation between negative and positive, but it's not total. They don't add up to 0, but they add up to this density, which you see from also in the case of Gaussian entire function. So for Gaussian entire function, you don't have these negatives at all, because analytic function has positive winding number around each 0. Okay, so that's what we can do with these 1-point intensities. I just write you the next result, which is yes.
Remark that for analytic function you cannot have negative. It's related to the fact that when you have equality in the Heisenberg uncertainty, it should correspond to the Gaussian, and in this case we have an analytic function. Yes.
I didn't understand the question, but I think still the answer is probably yes.
It's really that this 4c2 c3 plus 1 divided by 4 times square root becomes 1.
Yeah, so it's equality.
Yes.
You see that the rho 1 plus minus is exactly the same as the rho 1.
Okay.
And so you can
So this is the challenge.
Yes. Okay. So then we also looked at the variance of NBs, or N plus minus Bs, sorry. So that's what we can do. I'll write you the result. So another result. So now I assume that, well, this is a Gaussian Weyl-Heisenberg function, and now we have to make our life a bit easier. We assume that it's radial. This function h, which you see up there, it's a radial function. And then we look at balls of radius r, and r is going to be a big number. And then we are interested in these variances. And so we looked only at the variance of n plus minus variables. So BR. So the result is that this is big O of R. So this grows like perimeter of the ball. Usually this is called hyperuniformity. This is some kind of charge hyperuniformity. Hyperuniformity usually means that this growth of a variance is smaller than r squared, which is the volume of the ball. So these fluctuations are somehow around the expectation, are somehow suppressed at large scales. And we can also compute the limit. This limit, maybe you don't, I just write down the expression. So it's some limit which we can compute in terms of that h. Okay. I have still a few minutes. Maybe okay.
What is in the numerator? It's h squared or h prime?
H prime squared. Some ideas behind this. It's Kac-Rice formula in a more complicated form than in the with the expectations. But let's see. So then we look at this squared, that's the variance, minus the expectation. I just stop writing this b here, br maybe. B is br. That should be the variance. So we rewrite those a little bit. So first we write this term, and we separate the diagonal from the sum. It will be separate. Well, and on the diagonal I have this squared, and then because there are pluses and minuses, it's going to be 1 only. And then I know this was computed to be, I know the 1 point charge intensity, so this is 1 over pi squared b volume of b squared. Okay, so then some further rewriting. So this is the first term I can write with Kac-Rice formula gives me an expression for this first term. So it's going to be this. I use the heuristic form of my for my variable n plus minus b. And then, well, this is going to be the 1 point intensity, rho 1. So now it's like this is the one where everything is computed positively. So we have both things appearing here now. So I'm looking at plus minus variable here, but then I will need the 1 point intensity when everything is counted positively. This is b volume times volume of b, the second term, and then just this this one. Now, now this is going to be, then I work a little bit with that expression. Now it's a Gaussian integral again, but higher dimensional. Then I've got some explicit expression for this. I can bring this inside the integral, so I've got 1 over pi squared here. And to get this, I use Wick formula. I'm not going to tell you what it is, but it helps you to evaluate this. It's still pretty complicated, but it's better than not using Wick formula. Plus rho 1 of ER. Now there is this general lemma which says that this kind of expression is going to be O of R, exactly what we want, if so under this kind of identity. So I have this function tau, I integrate this thing, and it's in fact very quickly decaying function, this guy. This is supposed to be minus rho 1. If I have this relation, then this integral will have a leading order exactly that term, and they will cancel, and then the remaining stuff will be of order R. That's some well-known lemma. I don't know who to attribute this to. For example, there is a paper of accumulated spectrograms of Abreu, Romero, Gröhenig, Romero. So then the work is to show this identity. And then, well, in the paper we showed it with working hard. So basically you find this becomes a one-dimensional integral because of the radiality of h, and then you work and work and work, and then you find a primitive function for it, and then you see that the integral holds, which gives you this order of growth. Okay, I have nothing more to say. Thank you.
Just a silly question on your very last thing. So I guess this trick you can use to rewrite as an integral over BR times the complement of
This trick.
yes.
Yes, something like that, yes.
The fact that the R square doesn't matter is sort of natural because you integrate over two different divisions and then the
Yes. Yes, this is, yeah, it's some thinking like that.
how to use the fact that you could count also in the complement and
What do you mean?
I mean you count the number of n plus minus in the bond, right?
Yes.
And you know the number in the total
well, the number is infinite.
Yes, but somehow it's fixed. So I mean,
Ah.
it's like a trick, like you use the fact that the total number is conserved in a way, and you just say that the number in the ball is like the total number minus the number in the complement. So if you had
Sounds interesting.
If you had this finite, this would be, you could bypass this, but I don't know, and if in your case it works.
Sounds interesting, but I don't. Yeah. Okay.
Maybe I have one. Do you think it would be possible to compute the ρ2, the pair general, the pair correlation function, and characterize the repulsivity, possibly repulsivity of the universe?
Yes. Well. ρ2 is essentially here.
Right here.
Yes. But then we assume that this H is radial, this covariance kernel. That's a restriction. So
Yes.
generally you can compute it, but then it's gonna be complicated.
So you say it's hidden in the tau, which you didn't.
Yes, it's in the tau. Yeah, I didn't write it. It's quite massive, but it's an explicit. Yes, that's for plus and minus. When you cancel pluses and minuses, it's a bit more complicated, or a lot more complicated when you don't do it, because then you have absolute values in this thing, and then basically this thing doesn't work so nicely, and then you are kind of it's more complicated. Yes.
Are there still some other windows than the Gaussian for which the point process is isotropic?
You mean rotation?
Yes.
Hermite functions are only windows.
Yes.
Yes. But you can.
More exotic ones?
Sorry.
Are there more exotic ones? Or
More what?
exotic?
Exotic? Well, you can, of course. For example, you can. Well, I guess they tend to be like some kind of combinations. What you get with Hermite functions, you get. Yeah, I don't know. You can, for example, take two independent noises, and then you can, with different Hermite functions, you can make some kind of averages, and then still you have that. But yeah, but it's a restriction, yes.
What are the kinds of windows that applied signal processes would like us to study?
Well, that's not a question that I can answer, but maybe there is somebody in the audience.
Compactly supported windows, most likely.
Sorry?
Compactly supported windows. most
Yes.
likely. So some hand window.
Because this already opens the way to a lot of different windows.
Yeah, sure.
But trying to think of an intersection of windows that are interested from an applied signal processing point of view and from a spatial statistics point of view, like in the interest of building tests and construction.
Yeah, maybe this variance is more of a theoretical interest, but maybe the 1 point intensity can, I don't know, maybe that can be used somewhere, but that's not, that doesn't require this restriction.
Your windows here have to be smooth, right? They have to be Schwarz or...
Yeah, I didn't pursue the thinking what is the absolute minimum what you need. I'm not sure how far you can push this. Well, but yeah.
So you will need, I think, that this ambiguity function of the window will need to be something C2 at least.
C2 would be.
C6, I think we discovered is sufficient for all the all paths being C2, which you also need.
Yeah.
But you might be able to minimize the restriction.
Yeah.
Okay. I think that's the end of the discussion.
Yeah.